Good afternoon, everyone. Welcome back to session 2 of the digital engineering track. It is my pleasure to introduce Dr. Bill Rouse, CERC Research Council member and CERC Fellow in the Office of the Senior Vice President for Research at the McCourt School of Public Policy at Georgetown University. Dr. Rouse is a researcher, educator, author, and entrepreneur. He was also my doctoral advisory board chair member, and I'm very, very honored to be here to listen to him present on his updates for his research. And for the sake of brevity, I'll just stop here and he will be presenting updates on the CERC research task ART-005, Methods for Integrating Dynamic Requirements. With that, I turn it over to you, Dr. Rouse.
Thank you, Jan. I appreciate that. This is a report on a 2-year project that's on the home stretch. It ends in a couple months. And we basically focus on the question of how do you develop investment strategies when you have extreme uncertainty, when you're not really sure what the mission is, and you're not really sure if you have the technology to satisfy the mission. How do you navigate those uncertainties? We've done 3 case studies. The first one is focused on investments in driverless cars. The second one focused on policy portfolios to address the impacts of global warming. And this third one, the third case study, is focused on portfolios to enhance the STEM talent pipeline. Next slide, please. So we're going to first start off. So this is all a case study. I'm not going to give the background that I gave last year on the methodology. This is an application of that methodology. We're going to talk about the objectives, the stakeholders, what policies we're considering, what mechanisms, and on to reaching some conclusions about what would be the best policy portfolio to improve STEM talent pipeline in the United States. Next slide. So this is an interesting RT in the sense that our case study involves applying the ART-005 methodology to the 1042 problem. So we're actually picking another RT as our context. And the question is, how do we form alternative policy portfolios to enhance the STEM talent pipeline for both the DoD workforce and the US workforce more broadly? And how do we provide a means for stakeholders to interactively create and explore alternative policies and portfolios of policies? Next slide, please. So the stakeholders in this study, of course, are students, both existing STEM students and potential STEM students, the educational institutions offering STEM programs, industry employers, DoD employers, and then a super stakeholder, if you will, that decides the relative importance of the other stakeholders so we can look at trade-offs across who counts and how much they count. Next slide, please. So what do we mean? Here's some general policy interventions. If you intend to do X, you are granted Y dollars. If you're going to do X, you get Y dollars to pay for support. If you accomplish X, you get Y dollars in student debt relief. The institution is paid for delivering X if Y is achieved. Now, the specific instances we're going to look at in this case study is one is providing financial incentives to increase STEM student retention. The reason this is of interest, about 50% of STEM students drop out of STEM before they finish college, and they may just drop out of college completely. How could we get that percentage up? Investing in adopting of advanced educational technologies, many of which are maturing quite rapidly in the current environment. Supporting alliances among K-12 community colleges and industry to get the school to employment pipeline working. And then improving the performance of K-12 to produce STEM-ready graduates. So next slide. What's the mechanisms? Okay, well, we can communicate people about policies. We can educate them how to take advantage of policies. We can incentivize them, provide payments for enrolling, for example. We can invest and provide capital to create offerings and student support services, or we could regulate and require institutional participation to gain the resources involved. Next slide. So what are we uncertain about here? We're not exactly sure what workforce needs there are that would not be met without interventions. We're also uncertain about the efficacy of interventions and their costs, and the efficacy of the mechanisms whereby the interventions are implemented and their costs. And we have to look at the distribution of number of successes. So there's a probability function here that looks at how many people succeed in what we're trying to do. Next slide. And this is all handled by a binomial distribution buried beneath all of the computations. Next slide. So what do we care about? We care about the number of graduates over time, the program enrollment over time, the employment opportunities over time, the employment compensation, the tax revenues with the multipliers, because people who pay taxes also consume, and the people who get those consumptions also pay taxes. And the portfolio costs and net present value would be how we'll look at collapsing metrics over time. Next slide. So overall formulation is done with this data model. We look at the stakeholders that I mentioned earlier and what they care about. Validity is, do you actually have a good solution to the problem? Acceptability, is it a solution that people embrace? And viability, is it worth it to do it? Our interventions have impacts on those attributes, and the interventions can be put together in terms of a portfolio of policies. So the next slide. And here's where we get the information to do all that. How do we fill in everything in that data template? Next slide. So, case study of retention policies. What can you do to retain more students in STEM than the 50% who are currently retained? Well, one thing is pretty clear. You could recruit better students. You can make your criteria for acceptance much stiffer. This works. Basically, we found, and we have lots of data, if you graduate from high school with a 4.0 average and 800 math SATs, you'll succeed in college no matter what you do. Okay, but that's not everybody. That's only a small portion. So we could attract better students, but that's the problem with that is we're leaving out a lot of students. We could implement student support. We could actually provide support services, tutoring, advising, and other services to support students in their college career. We could redesign processes. A lot of processes within college curriculums are very inefficient, especially in STEM, where there are all these connected prerequisites. And so if a student misses one course or can't get into one course, that may lengthen their college stay by a year or 2 years because they have to wait around to get into the sequence again. And we could do a combination of 2 and 3 together, which is 4, support plus process. We're only looking at 4 stakeholders here: students, institutions, employers, and DoD. Next slide, please. So here we have some more detail on the support and process redesign: remedial courses, individual tutoring, expert advising, staff training. Interestingly, a significant proportion of students come to college unprepared to compete and to perform in college. So the remediation is important, the tutoring. The process redesign would be loose constraints, modularizing the course structure. Why do we think that a course has to be a semester long? Why can't we have modules and combine modules to get course credits? Credits earned module by module. And selected modules, of course, could be offered online. And then online courses to eliminate class size limits. A lot of freshman and sophomore classes are so immense that people can't get into them. And there's also some detriment of taking chemistry when there's 500 students in your class. The motivation is difficult to engender. Next slide. So we're going to narrow our attributes down to acceptance rate, retention rate, graduation rate, the time it takes for faculty to do it, the institutional costs, what is the net STEM talent resulting, and what are the net policy costs. Next slide. And we're going to use utility functions to represent how each stakeholder cares about those attributes, as shown in the next slide. In the next slide. There we go. Here we go. So students would prefer to have a high acceptance rate. Institutions prefer to have a low acceptance rate because that's part of the way they're ranked. So we have an interesting trade-off there. Retention rate, everybody would prefer, students and institutions would prefer higher retention and higher graduation. Institutions would prefer if faculty spend less time to support students, and institutions would rather not invest in having to do this. And you can see the shape of that curve. They really don't want to spend very much. The STEM talent is of importance to employers and DoD and is just an increasing linear function. And policy costs, DoD would rather spend less if they could. So that's our multi-stakeholder, multi-attribute utility model for this problem. Next slide. And then here are just the functions that we use to populate the model. Next slide. So here we have the attribute levels for the 4 policies. So for the better students, the acceptance rate is low. Student support is moderate. Improved process is moderate. And support plus process didn't make it quite so well through the translation in PowerPoint here, is high. It'll be high if we do everything, full court press for all students. Retention rate will be high if we only have the better students. Obviously, we're not going to have a retention problem. It's moderate in the middle 2 and high in the end. Graduation rate high, again, same thing. Faculty time is low if we get better students because they just don't need help. And institution costs are moderate, except for the far right where it's high. STEM talent is high on either end and moderate in the middle. Policy costs are very low in the first column and moderate in the other 2 columns and high in the support plus process column. Next slide. So then we tried doing different attribute levels where high is either 0.9 or 0.7. All the scales are normalized to be 0 to 1. Low is 0 to 3, and the a moderate is 0.5. The utility functions were varied across stakeholders. So students' retention, value retention and graduation rates, institutions value faculty time, et cetera. See, this is what basically a summary of the chart I showed you. So then we go to the next slide, and here's our multi-attribute model. We have the utility function of each stakeholder, and then we have the utility functions across stakeholders. So basically, each person, each type of stakeholder, say student versus institution, values different attributes differently, and they place different weights on those attributes. Overall, we get to decide which stakeholders are most important and which are lesser important, and you'll see how we vary that. Okay, but this is pretty standard multi-attribute utility stuff. Next slide. So here we have the results, and the black is where students are weighted 0.7, and the other 3 stakeholders are weighted 0.1. Dark gray is where institutions are weighted 0.7 and the other 3 stakeholders are weighted 0.1. The light gray is where employers are valued 0.7 and everybody else is 0.1. And then the lightest gray is where is for the hybrid. Lightest gray is where DoD is valued 0.7 and everybody else is valued 0.1. So you can see we got some variation here. The next slide gives us some summary of this. Recruiting better students is preferred by all stakeholders other than students. Okay, the yields better STEM graduates and requires less investment. Now, you might think this is maybe a little unusual, but if you look at the top schools in the country, the absolute top tier 1, this is exactly what they do. They recruit the best possible students and are able to enroll them, and these students do very well without much of an investment. Okay, the problem is, of course, from a STEM workforce point of view, we're not getting enough students in the pipeline to support the workforce. The hybrid one in the far right, we have student support plus process improvement, is improved by students and is a close second by employers. It basically provides success opportunities to much more students, but it requires institution and DoD to invest. In this case, where the employer is not investing. And so that's one of the reasons the employer is in favor of hybrid. The support or process by itself gives only moderate returns. This assumption warrants some careful reconsideration. We're not sure that we've got the right estimates there, but I think the 2 extremes, better students or hybrid, is what you might expect. Next slide. Okay, now I haven't really talked about uncertainties here, and that's the overall project is about managing uncertainties. So let's look at this. Next slide. So what are we uncertain about? Well, we're certainly uncertain about the extent, the effectiveness, and the costs of student support and the extent, effectiveness, and costs of the process redesign. So there's a lot of uncertainty there. The other thing is we could invest in other things other than what I've just worked out, not just retention. We can invest in adopting of educational technologies, which are maturing very quickly. We could address potential alliances with K through 12, community college, and industry. And when I talk about 1042 later this afternoon, you'll see that there's some very impressive things going on, in this case, in the state of Connecticut, of how they're dovetailing K through 12, community college, and industry. And I won't go into that right now, but that's a very real and tangible option. And we could increase K through 12 production of STEM-ready students. However, this would be one of the most difficult things to do because the K through 12 system throughout the United States is very uneven. And basically, in order to be STEM ready, students have to have Algebra 1, Algebra 2, geometry, trigonometry, et cetera. And there's a significant percentage of high schools in the country that only offer Algebra 1. That's it. That's the highest level course. What that means is that a big percentage of students in the United States cannot become STEM ready because there's no content to support that. So this is a very difficult one to consider how to fix. Next slide. So we've developed in the past a way to look about how do we manage uncertainties. If our objectives, dynamics, and constraints are measurable and tractable, then maybe we can find out what's the optimal allocation of resources and basically optimize. However, in many cases, we don't know that. We don't know the objectives, dynamics, and constraints. In our studies of educational data, there's huge inconsistencies and deficiencies in the data available to support some of these things. But if your response time is less than the external response time, you could just wait and adapt. Wait and see what happens and adapt at the time. Maybe you have multiple viable alternatives, futures, and you can describe what these futures might be, and you could hedge, you can make small investments, buy options on each of these futures. But if you can't do any of those things, you just have to accept. Accept means just waiting and seeing what plays out because there's so much uncertainty that you just can't know how to act. Next slide. So how do we think about this? Well, we've got uncertainty about requirements, and we've got uncertainty about the technology and the costs. What should we do? Well, if we have complete certainty that we need something and we know exactly how to do it, we should optimize. We should optimize that educational capability because we know. If we're not sure we need it, we could adapt. As I move down the right column down to the second row, we could adapt when the requirement emerges. And if it's just not required at all, but something we're good at, we could archive maybe for potential later use. If we go into the top of the middle column, if we know that was going to be definitely required, but we're not sure how to do it, then we're going to have to hedge via an R&D investment so that we can create that capability, even if it's possibly required. If it's not required, then we just accept where we're at. If it's definitely required, but we don't know how to do it at all, then we're going to have to hedge via a partnership. Same way with the next cell down. And again, if it's not required, we just accept. So we have a mixture of how we can invest here in this portfolio. Next slide. Okay, so let's look at our STEM policies. Relative to retention investments, we think it makes sense to optimize. The target population and the needed interventions are clear. There's some uncertainties, but what we need to do is clear. And the incentives for co-investments from other players are likely going to be successful. So if the government provides bonuses for people being retained who wouldn't have been retained, institutions will be incentivized to make those investments. We think we should adapt to trends in educational technology, exploit rather than invest. This is all moving so fast with so many big players. There's no need to try to start and do this from scratch at all. But we should focus on the accessibility and efficiencies of the educational technologies. If we look at the alliances of K through 12, community college, and industry, and as I said, this is a pretty exciting alternative that I'll elaborate in my other talk this afternoon. There are many alternative scenarios. There are a wide range of barriers and hurdles when you try to get everybody across a state, all the high schools, all the community colleges, and all the employers to cooperate. Even though they're enthusiastic about it, it can take quite a bit of effort to do that. So we're thinking you can hedge with those potential alliances. Right now, we're looking at expanding from Connecticut to include South Carolina, for example. We just accept the state of K through 12 education. It's extremely uncertain, highly expensive to fix it. As you probably, most of you know, K through 12 education is locally controlled by school boards and there's some impact from the state, almost no impact from the federal government. There are no national standards for graduating from high school. So this would be very difficult to try to change this. We should pay attention to it. And in this case, our investment strategy is accept. So next slide. So think about what we accomplished here. The question is how to improve the STEM talent pipeline. There are a variety of things you could do. And you might think about picking one of them and making a major investment and see if you can achieve that. However, we don't think that's the right answer. We think you should have a portfolio of investments. Some of them are larger, some of them are smaller. You're hedging against your uncertainties so that when the uncertainties play out and you figure out more of what's going to happen, you're prepared to actually proceed. So the idea that an investment decision making is either yes or no doesn't make sense in this environment and in many environments. Same thing with energy, same thing with driverless cars. We need to figure out what's the portfolio of investments and what part of the problem those portfolios are intended to improve and how they actually help you to manage the uncertainties. Thank you.
While we wait, I have a quick question. Do you have any follow-on work from this interesting topic?
Well, yes, we do. This topic has grown as we become smarter about it. In fact, I just came from a meeting at the National Academy just before this meeting. We're looking at launching a major initiative to focus on education ranging from preschool through K through 12, through college, to employment. This is a major national challenge.
Yeah, that's great.
And the interesting piece about it that I had not thought about in advance is the skilled technical workforce, the people who will operate, maintain, produce complex systems, isn't going to be everybody with engineering degrees. It's going to be a lot of people with, say, an associate's degree in some particular specialty. And the question is, how do we actually get the whole system to work that way? Because what's happening is employers are saying, one employer said, I need 200 welders and 200 electricians, and I can't find any of them. Well, the interesting thing is these are well-paying jobs.
Yeah.
So if we can prepare people for those kinds of jobs, there's tremendous benefit, both to the work, but also to society.
Do you think it's also a perception that the jobs, blue-collar versus white, and people are hesitant to take some of those jobs? What can we do to improve that?
Well, these really aren't blue. I mean, some people call them gray-collar jobs. Another possibility is they call them new-collar jobs, where your specialty is to deal with the complexity of cars, the complexity of manufacturing, the complexity of healthcare. And we need you when things go wrong. And your job is to figure out what happened and what to do about it. I did some back of the envelope projections that there's going to be 25 million jobs, new jobs like that.
Wow.
According to the Bureau of Labor Statistics, the two fastest growing jobs in the country are solar panel installer and wind turbine maintainer.
It's fascinating.
So, yeah, there's a lot of really great opportunities, but people, they can't just come out of high school. And certainly if they don't have any education, they can't possibly do these jobs.
That's true.
So we actually need to train and educate people to be able to do the things we need. And everybody benefits, including them, of course.
Yeah, great. Thank you. Any other questions or comments? So we have one from Marilyn Pineda. This is, as you say, a national priority. What outcomes do you expect to have? DoD investment separate from the traditional education systems?
My sense is the investments are going to be more widespread. I think DoD can seed a lot of these activities to get them going, but there's going to need to be investments by the K through 12 system, by the community college system, by employers. This is going to be state level investments, not all national level investments. I was talking recently with the president of the South Carolina Chamber of Commerce about the skilled technical workforce and how do we actually create the people to fill these jobs. And he said, that's the number one problem in every state. So I think DoD can seed it. I don't think DoD needs to think they have to pay for the whole thing. There's a lot of beneficiaries here and a lot have resources to invest for the right outcomes.
Comment, Michael McLendon. STEM initiatives needs to also include technical colleges and those who are not interested in what we think of as traditional engineering degrees, etc.
I totally agree. I totally agree. We're focused as well on technical colleges, on community colleges. People for many of these jobs don't need an engineering degree, but they need some engineering knowledge and skills. They need sort of equivalent maybe of an associate's degree. This afternoon at 10:42, I'll talk about a program in Connecticut where the high schools and community colleges and employers are working together so that a high school freshman can decide to go along a certain track. They will be trained to work for Northrop Grumman or Sikorsky or Pratt & Whitney, whatever. They'll get the right skills. They'll graduate from high school with an associate's degree. They'll have a 2-year degree when they graduate from high school and guaranteed enrollment in a 4-year degree if they choose it. At the same time, they're going to have guaranteed employment for a well-paying job in the defense industry or in the automotive industry, for example.
We also have another comment from Nick Justice. It shouldn't have to pay for them, but structure to define the pipeline would help.
No, that's right. That's right. I mean, we've been working, and you'll see in 1042, we've mapped out the pipeline from preschool to employment over 20 some years. What are the things that happen, and what are the transition probabilities, and what policies might enhance those probabilities? I agree. It's not a question of DoD paying for the whole thing, but since DoD has a workforce needs, as does the country, it's important that they stimulate the right thinking and stimulate people to start thinking about how they can invest.
Question from Kelly Alexander. What should we be doing in early education to keep kids motivated before it's too late? By the end of high school, many students have tuned technical skills out as an option.
Well, let's start really early. I've got an interesting statistic that we learned along the way. If you finish 3rd grade, so you're 9 years old, you finish 3rd grade and you haven't achieved 3rd grade reading level, chances are you'll never go to college. Okay, so at 9 years old, your future is highly constrained. We need to focus on those early years. And there's been, I was in a meeting earlier today, a lot of effort of, okay, how do we instill engineering experiences in K through 12, even in preschool, because children love hands-on experiences. They love trying out science things. I think that that we need to start very early. If you look at what causes someone to choose engineering or STEM, one is because one of our STEM majors. That's the easy one. The other is that they have some role model that they aspire to. Maybe it's a relative or someone in the community. A third one, though, is they get STEM experiences early. They get to experience science, engineering, design, etc. And this is often very motivational. Without any of those motivations, no parents, no relatives, no role model, no experiences, students don't pick STEM. They don't know what it is.
Agree more. Thank you. Another question here. Do you think since education requirements vary state by state, so greatly that certain states will become more tied to DoD partnership? Any of those requirements or standards?
Well, Yeah, it varies enormously state by state, and varies enormously town by town. Local school boards can decide to not teach anything beyond Algebra 1, and no one's going to stop them from doing that. So it is highly locally determined. My experiences about the Connecticut program, which I'll talk about in 1042, is they were extremely proactive to get these pieces of the system work together. And now in our initial discussions with South Carolina, they're proactive too in somewhat of a different way, but I think it is very locally determined, not only at the state level, but at even the school board level.
Thank you so much. Thank you for all the great questions. I think that has led to some fruitful discussion here. And with that, I wanted to just give the audience some time if they wanted to move to different sessions. And if anyone else has any more questions or comments, I think Dr. Rouse is still here. Really appreciate your perspective on that. Another question I had was, how do you think we're tracking those? So for example, you're saying you're starting from possibly preschool upwards. Is there some efforts to track some of that to see
There
what
are tremendous efforts. We have tremendous data sets. But one of the problems we found is a lot of inconsistencies. Okay, I mean, and another interesting we found is that a lot of the data is surveys. What do the students think, as opposed to what was accomplished? I mean, did they finish a program? Did they finish school? Did they go on to an employment? It's really hard to put all the pieces of we have a lot of puzzle pieces. It's hard to put all the puzzle pieces together into one puzzle.
That's another opportunity for research there. Thank you so much again. Yeah. With that, I just want to, again, open it up if there's anyone who has any other final questions or comments.
If you go to the 1042 lecture, I'll just pick right up where we're leaving off.
That's right. That's at 4:30, I believe, at the Human Capital Development
right.
Talk. So that's a good segue there. Thank you again, Dr. Rouse, for your time. Really appreciate it.
Yep.
Question just came in from Leroy Hanneman. Could you comment on collaboration with potential re-inclusion of vocational training in extended academia?
The re-inclusion of vocational training in well, I think this program in Connecticut is sort of a good example of doing this. When I was in high school, I took welding, foundry, woodworking, and everybody had those opportunities. A lot of those things have been excluded. When I was in college, we actually had to design and manufacture products, go out in the factory and build them. And that got to be too expensive and too time consuming. But I think there's more hands-on, there's a thing called the makers movement. And it's on every campus where they have labs where people can build stuff. We had an interesting experience at Georgetown where we've been looking at creating an engineering minor in a school where there's no engineering program, okay, an engineering minor. And why would the students be very interested in engineering minor? It's because they go to the makers lab and they build stuff, and they would like to build stuff that actually works. So they want some engineering principles, practices, etc. and some techniques to help them so they can build real things. And these are, college students in a liberal arts program. So I think that's becoming, I wouldn't say pervasive, but it's more common that you see those sentiments.
Much again for your time, Dr. Rouse.